we're going to look at the series, the summation n equals 10 to infinity, 1 divided by n squared minus 4. And to determine if this series converges or diverges, we'll look at 3 different tests and see which ones are applicable and work the best. The first of these tests is the limit comparison test, which I'll abbreviate by LCT. The second test is the direct comparison test, or just a comparison test, which is CT. And the third test is the integral test, which I'll abbreviate by IT. So let's first look at the limit comparison test. We take the 2 series that we're comparing. One we'll call summation A sub n, and the second one we'll call the summation of B sub n, with the restriction that A sub n and B sub n are positive for all n. And then we look at the limit as n approaches infinity of an divided by bn, and say we computed that limit, and that limit is L. So if L is positive and finite, then the following must be true. Either the 2 series, the A sub n series and the B sub n series, both converge, or the A sub n series and the B sub n series both diverge. So now we look at our series, the series we're examining, the summation n equals 10 to infinity of 1 divided by n squared minus 4, and we'll call that our A sub n series. Now to select B sub n series, we do the following. Let d be the highest power of n in the denominator. That's, since it's n squared, d is equal to 2. Let capital N be the highest power of n in the numerator. The numerator just has 1 in it, which means it's n to the 0 power. Now let's look at the difference of d minus n, and we find that difference to be 2. Now select B sub n series. So since our A sub n starts at 10, we'll start this one at 10 as well, to be the simplest series with that property that the difference in the highest power, d minus n, is equal to 2. And such series obviously has to be 1 divided by n squared. And now let's compute the limit as n goes to infinity of A sub n over B sub n, and that's equal to the limit n goes to infinity 1 divided by n squared minus 4 divided by 1 over n squared. This simplifies to the limit as n approaches infinity of n squared over n squared minus 4. Since the highest powers are equal, the limit is the ratio of the coefficients, which is 1. This limit being 1, we can apply limit comparison test. So the 2 series, n equals 10 to infinity, 1 divided by n squared minus 4, and the summation n equals 10 to infinity 1 over n squared, both converge or both diverge. Now the series here, 1 over n squared series, it's not quite the P series. P series starts at 1, but this is a modified P series, and it clearly converges. So this is P series. It's okay that it starts at 10 with P equal to 2. So this series converges, and we can conclude that this series also converges, and this is by, of course, the limit comparison test. Let's try the comparison test. And the comparison test, we also have an A sub n series and the B sub n series, and they are the same as for the limit comparison test. So here is the summation n equals 10 to infinity 1 divided by n squared minus 4. This will be our n equals 10 to infinity A sub n series. And the summation n equals 10 to infinity 1 over n squared. And this is our n equals 10 to infinity B sub n series. Note the following. N squared minus 4 is less than n squared, and this is true for all n, but in particular, since our series starts at 10, it's clearly true for all n greater than or equal to 10. Then, by basic property of algebra, 1 divided by n squared minus 4 is greater than 1 divided by n squared. And so the summation n equals 10 to infinity, 1 divided by n squared minus 4 is greater than the summation n equals to 10 to infinity, 1 divided by n squared. Now here's where we see that the comparison test does not apply here. We can't use the comparison test by comparing these two series. Now this series converges, right? It's the same as before. It's a p series with p equal to 2, so this series converges. But the series we're examining is greater than the converging series. Now we don't know what it converges to, but it's a finite number. Let's say it converges to capital C. Well, all we know is the series summation n equals 10 to infinity of 1 divided by n squared minus 4 is greater than that number. It could be some other positive number larger, which means the series will converge. It could also go to infinity, which means the series could diverge. So if the inequality is pointing like this, if the series is greater than the converging series, we cannot make the conclusion about convergence or divergence of the series we're looking at. So comparison test by comparing these two series does not apply. And this is a common mistake that students make. They use the comparison test when the equality is facing in the wrong direction, and they make a mistake. So do not make that mistake, because inequality doesn't give us any information about convergence or divergence of the series we're examining. Now let's look at applying the integral test to this series. Let f of x be defined by 1 divided by x squared minus 4. This is for x greater than or equal to 10. This function is continuous, it is differentiable, and it is decreasing on that interval. That's all very easy to see. And if we plug in any integer greater or equal to 10 into this function, we'll get that term of our sequence, 1 divided by n squared minus 4. So integral test applies, and we look at the integral from 10 to infinity of 1 divided by x squared minus 4. Now how would we evaluate this integral? If you recall, look at the integration techniques. The way we'd evaluate this integral is by using the method of partial fractions. 1 divided by x squared minus 4 can be rewritten as 1 divided by x minus 2 times x plus 2. These are distinct linear terms. We can write it as equal to a over x minus 2 plus b over x plus 2. Now let's multiply both sides by x minus 2 times x plus 2, and we have 1 equals a times x plus 2 plus b times x minus 2. Let's plug in x equals to 2. Left hand side is 1. The right hand side is 4a. So a must be 1/4. Let's plug in x equal to minus 2. We have 1 equals minus 4b. So b is equal to minus 1/4. And so the integral of 1 divided by x squared minus 4 is the same as 1/4 times the integral of 1 divided by x minus 2 minus 1/4 times the integral of 1 divided by x plus 2, which is equal to 1/4 ln of absolute value of x minus 2 minus 1/4 times ln of absolute value of x plus 2, which we can rewrite as 1/4 times ln of absolute value of x minus 2 divided by x plus 2. And so the integral from 10 to infinity of 1 divided by x squared minus 4 is equal to 1 over 4 times natural log. Now we can drop absolute value because all the values of x are big enough that we cannot have a negative number inside the natural log. So this is 1/4 ln x minus 2 divided by x plus 2, and that's evaluated from 10 to infinity. this is equal to the limit as x goes to infinity of 1/4 natural log of x minus 2 divided by x plus 2, and then minus 1/4 times natural log of 10 minus 2 is 8 divided by 10 plus 2, which is 12. And let's look at that limit. That's since as x goes to infinity, x minus 2 over x plus 2 goes to 1. That's equal to 1/4 natural log of 1 and minus 1/4 times natural log. So 8 over 12 is 2/3. ln of 1 is equal to 0, and minus 1/4 ln of 2/3 can be rewritten as 1/4 ln of 3/2, or 1/4 times ln of 1.5. That's a positive number. This is a positive number, and more importantly, it's finite, so the integral converges, and this implies that the series n equals 10 to infinity 1 divided by n squared minus 4 converges by the integral test. So as we looked at the three tests, limit comparison test, that was fairly easy to use. We could not use the direct comparison test or comparison test, and we could use the integral test, but we had to use a partial fraction to integrate 1 divided by x squared minus 4. So of the three tests, by far the easiest one to use was the limit comparison test.